Okay, this is recording now. Okay, so yes, file import part. This is the stat file here. Double click. We rename this. They said to rename it strut. Import all parts, create individual parts. Yeah, that's all good. Okay. Then we want to partition this in the mesh module. So switch to the mesh module. Partition tools, partition face. Yeah, sketch. So we'll pick a vertical on the top. Okay. So we'll sketch out the partitions that are in the figure there in the assignment brief. Okay, middle click. Okay, that's our partitioning done. So we want to assign meshing type, so our mesh controls. Select everything. Middle click. So we want to assign quad structured. Okay. So now our global seating density says to 0.03. Okay. And then we want to assign local seating density or the seeds along the edges. So firstly, it says to have 6 uniformly spaced elements along each 90-degree arc. So you're probably familiar with this from doing your first assignment. So we want to select each arc. So I'm holding down the shift key while I'm doing this. Okay, that's everything selected. So now middle click by yeah. So it's just 6 by number 6. Okay, and now we can see that we'll have 6 elements in each of these sections. So then we want to do the same for the straight sections. So holding down the shift key and left clicking on each line. Middle click. So we want to assign a bias here. So it says to assign double bias by number 12 and 4. Okay. So the bias needs to go. So you want, more a denser packing of elements further away from the center. So we should have more elements here and more elements here. So the arrows are pointing away from the center. If that's not the case, you can just select flip bias select and then select on which line, and it'll flip it. So that's okay as is, right? So yeah, so you can see now, that's worked okay. So now we can mesh that. So middle click. Okay. So now we want to create an orphan mesh from that. So mesh, create mesh parts. Yeah, that's fine. So strut mesh 1 is the name that they use. So middle click. Okay. So this is our orphan mesh. So now we want to make this solid. Run through apart. Mesh, solid layers, and select everything. Okay. Okay, so total thickness 0.15. Number layers 4. So you need to click this button and click so share nodes between each layer, and delete base shell elements. So delete this is your base shell. So make sure that you have all of these ticked, or it'll give you problems later on. So okay, so now we have our solid part, or a solid mesh. So you need to add a y-axis, or an x-axis and a y-axis. Yeah. X-axis, y-axis. Okay, so now in the assembly module, we're going to use the plugin wrap mesh. So we bring in the instance strut mesh. Okay, and you notice there is no option to make it dependent or independent. It's just going to be dependent. Okay, so we use our plugins, tools, wrap mesh. Okay, so we need to select our circumferential direction. It's this one. Axial. The name is strut wrapped, and the wrapping radius is 0.57 649 63 764 163. Okay. Okay, that worked. Okay. Again, if anybody sees me missing anything, just let me know. Okay, so now we need to go back and we want to change the element type. So we can go back into the mesh module. So we have the part that we just created with the wrap mesh plugin, so strut wrapped. So we want to change the element type. Select everything, middle click. So it is this element C3D8I. If you're ever quoted an element and you're not sure what it is, you can just Google that and it'll come up. But this is basically the element that we have, C3D8OR. But the incompatible modes are not reduced integration. Okay, so that changes C3D8I. Yeah, that's good. Okay. Okay, so that's that. So now we want to create the next part, which is the expander. So it's called expander, and it is deformable shell revolution approximate size. Cool. Okay, so you just draw that out as is in the figure there. So 424.963 e to the minus 3. 4.963. Yep. Okay, middle click. And the length is 1.6. Okay, so middle click again. Revolve through 360. Okay, there we go. So now we want to mesh that. Mesh. So first of all, apply global seeding density of 0.05. 0.05. Okay, and then we want we basically want it one element lengthwise. So we can use that using seed data still. So no bias, and by number 1, so one element. Okay. So mesh the part, middle click, There we go. So you see one element tick, or length, or whatever you want to call that. So then we need to change the element type again. Okay, so we have this SM, SFM, whatever. So this is a surface element. Yeah, so at the moment we have a shell element. See here. Yeah, shell, but we need to switch to surface. And reduced integration, I think, yeah. Okay, so this should match now. So SFM 3D 4 or. Yep, cool. Okay. So that's part one. So part two, materials assignment. Okay. So first of all, we go into the materials tab or properties tab, create a new material called stainless steel. Stainless steel, and it's elastic plastic. So first of all, add the elastic block 19300 use modulus Poisson's ratio 0. And now we add in the plastic block. So again, this is modular, right? So you can keep adding blocks here, and the material will become like so elastic block, elastic plastic material, which is quite standard. So we have 4 entries here. 301, or sorry, 304, 0.0928, 0.17, 40, 0.332. Okay. So now we need to create our sections. So first section we need to create is stent, called stent. So the section that will apply to the stent. So this is solid homogeneous continue. And there's only one material that we've made, so okay. Next section then is expander, and this is a shell and surface. Okay. You can leave density out. So now we assign these sections to each instance. So first of all, for the expander, so assign section says to create a section called all. So we can do that in the process. Click on this, middle click, and there's only one option because it knows that we made this part as a shell, and we have only one shell section. Okay, so now we do the same for strut wrapped. So again, this is going to be called all. Select everything. Middle click. There's only one option because we only have one solid section. Okay. Okay, and then that's confirmed by the change in color. Okay, so that's actually that section done. So analysis steps. So first of all, to kind of just set us up for the analysis and assembly, you want to create a number of sets and surfaces. So that's done in the part module. So select the expander. We're going to create the surfaces for that first. So we want to create an outer surface here that's representative of the outer surface of the expander. So tools, surface, create, and it's just going to be called outer, geometry based. Yeah. So we click on this, middle click. So now we want to select the face that is the shell. So we're going to select purple. I know it says here select internal faces, but just think of this as whatever face you're going to use in your analysis is usually the face that you need to select. So purple. And I'll just see how that looks. So parts, that's going to be, so that surface is going to be in parts expander, surfaces, outer. Yes, so the outer surface is highlighted. Okay, so now we want to create some surfaces for the strut. Okay, tools, surface, create. Mesh is the only option because this is a mesh. So the first one is inner. Continue. Okay, so to select the entire inner surface, we can just change to biangle and middle click. Okay, so now we want another surface that is inner. Sorry, actually, I think I named that wrong. That should have been inner. You just rename that. Oh no, wrong one. Surface. Oh no, my bad. That's good. That's the inner surface. Okay, so now the outer surface. Surface, create outer. Middle click. Okay. So now two more surfaces. Tools, surface, create, and one. Middle click. Tool, surface, create, and two. Continue. Okay. Okay, so then we just want to create a set that we're going to use as like a constraint. So tools, set, create, pinned, node, continue. And okay, so we need to switch to select nodes individually. And it's this pin here, or it's this node, so just bang in the center. Middle click. Okay. So that's that there. Yeah. Cool. So just add a datum to this as well. Z. Okay. Okay, so now we can go about assembly. So this is done in the assembly tab again. So we want to replace this instance. So instance replace. You can just delete it and add in the other one, but I'll just follow this. So select an instance to replace this one and replace with strut wrapped. Okay. Yes. and then rename that. Assembly, rename, strut. Okay. So yeah, now we can add in the expander. Okay, and now we can add our constraints. So first constraint is an edge-to-edge constraint. Edge-to-edge. So select a straight edge on the movable instance. So the expander is going to be the movable instance, and a straight edge on the fixed instance, which is the stent. And okay. So now we want to center this stent on the expander. So we can do that with the translate instance tool. So select this as our instance. And now we need to select a start point and an end point. So I'm going to select this as the start point and this is the end point. So it will shift the whole stent across. So just to do that, I'm just going to hide the expander. Expander, remove. So select instance, design, middle click, start point. Okay, middle click. Oh, sorry, I actually made a mistake there. I'll just do that again. Translate instance, left click, middle click, select the start point, and then select the end point. So the end point is on the expander, so I'm going to bring the expander back in. This. Okay. Okay, so now we just need to shift the stent across a little bit. So we're going to do the same thing again. So translate instance, select this our instance, middle click, starting point. I'm just going to hide the expander again to select that. Remove. Starting point is here. Ending point is here. Okay. Okay, so that's shifted across. Okay, so that's the assembly done. So now we set up the analysis in steps. So there's a number of steps. So it says, first of all, so by the way, I know I'm kind of working from this tab now. I think in the last few, I was kind of doing everything in the tree here. Both are the same, and you can kind of work from either. So for instance, I'm creating a step here that could also be done down in the steps section in the tree. So steps here. So I could right click on that, create, and then I'm going to create my boundary conditions in here as well in the load and interactions module. So those boundary conditions could also be created in each individual step here, or kind of just created generically down in the interactions loads boundary conditions. So there's three different options there how you can define things, and actually up here as well. So step, create. So there's 4 different ways of creating a step, which might be confusing, but okay. So the first step it asks us to create is expand, static general. Okay. it asks us to put in a description, which you don't really need to do, but I'll just put it in. Extent expansion, NeoGeom on. First step size 0.1. Okay. Then 2 more steps. Recoil. Okay. 0.1. Okay. Pressure. Okay. Okay, so that's our 3 steps created. You always have an initial step. So expand, recoil, and pressure. So now we're going to create our boundary conditions. So that's in the load module. Again, you can create them here, create, or here, create, and then it'll be a manager. Okay, so we want to create a new cylindrical coordinate system. So to do that, I'm just going to put in a few datum points, which are just going to help me do that. Datum points midway between 2 points. You'll see how I'll use these in a second. Okay, so that's 1. Okay. Yeah, so you can create your datum the same way, your cylindrical coordinate system here, but in the module brief or the assignment brief or whatever they do it here. Or sorry, not here. Here, same thing. So cylindrical is going to be called C Y E. Yeah. Continue. Okay, select a point to be at the origin. So I'm going to use this one. Select a point on the radial axis. Oh, here. And select a point on r theta. Okay. I'm actually going to move this rectangular axis here to the center as well. You don't need to do this, but I just prefer it to be out of the way. Rectangular. Okay, and that's actually, those coordinates are fine. If they're not fine, you can go through these steps, but I'm just going to skip through all the steps that we did last time, like selecting a point on the y-axis, x-axis, z-axis, and so on. So create datum. And I'm just going to delete that datum. Where is that again? So it's features. that one. So see it's highlighted there. Yes. Okay. So now we have that cylindrical coordinate system in place. So it says to create a boundary condition named expand. Named expand. And it needs to be in the expand step. And displacement rotation. Okay. So we want to select the set, expander all, continue. So U1 goes to 1.5. So we're expanding radially. 0, 0, 0, 0, 0. Okay. Yeah. Oh yeah, and then sorry, I forgot this. We need to select our new cylindrical coordinate system. So okay. And yeah, so step expand. Yeah, that's all good. Okay. Okay, so you can see that now. So next boundary condition then is we want to confine that set called pinned on the strut. So same as create boundary condition, pinned in the expand step again. Yeah. Displacement rotation. So this one, you can highlight this, take this here to visualize the set that you're clicking on. Continue. Select our cylindrical coordinate system again. Okay. And U2 and U3 go to 0. Okay. So then we want to create a load called pressure. So pressure in step pressure and pressure here. Continue. So this is going to be defined on strut outer surface. Strut outer. Continue. Magnitude is 0.25. Okay. Okay, so there you can see that visualized. So now we want to define some interactions. So switch to the interaction tab. Again, last time we did this down here. We defined interaction properties. Remember, we defined no friction usually. And then we defined interactions between two surfaces, but we're going to do it here this time. So first of all, we're going to define two reference points. It's important here. You can also go tools, reference point. So you see there's loads of different ways to do it, which probably makes things more confusing, but once you get used to it, it's handy. So our first reference point here, and then second one is going to be here. Okay, middle click. So let's make this interaction here. So this interaction is going to be like a symmetry interaction. So this is only a section of the stent. It's one strut, if you want to call it a strut. So this is going to be called cyclic. See. in the initial step. Cyclic symmetry, continue. And then we want to select that surface end1 as our master surface. End1, which is highlighted there. Continue, and then the slave surface is end2. Continue. So we want to then select like constraints of where this is going to be, where this symmetry is going to be confined to. So the reference one, and reference 2. So selecting viewport, geometry, reference 1, geometry, reference 2, and number of sectors is going to be 6. So this is a 6th of the extent. Okay, cool. And you'll see that visualized later on. So lastly, we've one more surface to surface constraint. Yeah, so contact, and this is in the expand step. Surface to surface, contact standard, continue. Select the master surface, so it's going to be the surface of the expander outer surface. Expander outer, continue, and then the inner surface of the stent surface. Strut wrapped inner, continue. Okay, so we haven't defined an interaction property here, so we could have done that, you know, define interaction properties, and it would be in this list, but we can also just do it here. So frictionless, contact, continue, mechanical, tangential, frictionless. Okay, so that's defined. So we want to just disable that in the recoil step. So we can go into interactions manager, contact. We want to disable that in the recoil step. Deactivate. And you can see there that's also deactivated in the pressure step, and there's no option to reactivate it, so that's fine. So dismiss. So that's everything. So now we create our job. Create balloon. Balloon expanded. Continue. Okay. Submit the job. Okay. Right, completed. You can look at the results through this, or you can just go into the visualization tab. Okay, so here it is. So to visualize contours or whatever, click this. Okay, so this is the expander. So we want to just run through this now to see if it worked. And look, it has worked, but let's just run through it. So the different steps. So you remember, so first of all, we have our stent and our expander. Nothing's happening. Then the expander expands, expanding the stent. and then there's a recoil step, which I guess is there, and then there's pressure on the outer surface of the stent, which is there, and that's our analysis. So we're going to hide now the expander. Expander. Remove. Okay. Yeah, nice. So that's only a sixth of the stent. So now we want to just visualize the whole thing. Yeah. So view. ODB display options. Mirror. So we want to select our cylindrical coordinate system and display all 6 segments. Apply. Okay, so there's our entire stent. So let's run through that. So that's the entire stent. And there's it expanding, recoiling, and pressure. Okay, so that's really it. So the last bit, unfortunately, we're not going to be able to do. It requires a plugin, and I realized these versions of Abaqus don't have that plugin. I've reached out to Abaqus to try to get it, but it'll probably take a day or two if it's still available. So it's a Goodman diagram or a Goodman evaluation plugin, which is basically just a fatigue analysis. So it'll run this stent through either a number of different stresses, within a certain range, or a number of different strains within a certain range, and try to predict kind of failure, fatigue failure, through that. But yeah, the plugin would be in plugins, tools, and then there should be Goodman evaluation, but it's not there. You might actually check just whenever you guys are doing this yourself. If anybody sees it there, let me know, because then I can steal it off that computer. So if you see Goodman evaluation here, let me know, and just let me know what computer it is, and I'll try to steal it off that, and so everybody can have it. But yeah, so that's it. There's a quick one. Any questions?
I have a question about the write-up for the last week's tutorials.
The Abaqus one.
Yeah.
Yeah.
Just like you saying that you don't want a step by step for the method. What sort of things do you want in that kind of?
What, like for the methodology, like?
Yeah.
Yeah. I guess you need to say, like, I just go back into the mesh tab here, right? So yeah, so you're changing you're changing for, so there's 3 different things, if I remember, that you're doing, right? So you're changing element density on a global level. So I'd say that's one thing. So say that you changed element density by oh crap, I can't see that. One sec. Element density by varying seeding density, and then kind of how you, so that's one thing. Then the second thing, what you would have varied is the element type. So just say you varied element type. I can't remember what it was. It was reduced integration v incompatible mode or something like that. So mention what you're changing there, and kind of what's the difference between each of those elements. And then the third thing was to change local seeding density. So just kind of briefly mention how you do that. So you're using a bias to do that. So let's click on one. So yeah, so you say, you know, what bias you used, bias ratio, number of elements, and so on, you know. And then that's kind of your methodology in changing your mesh. And then the second part you need to talk about is what you're analyzing. So I said the best one to probably do is just visualize in your results, is to just visualize max von Mies stress. So just kind of talk about that, you know, what's that representative of, but definitely don't go into like, you know, to visualize this, you click this button, then you click this button, then you click that button. I'm not sure if that's enough help, is it, or?
Yeah, that's perfect.
Yeah. The other question.
Yeah.
I sent you an email regarding like the failure of Abaqus earlier. I don't know whether I've seen any email from me.
Sorry, I've been haven't got to my email yet.
Because what I did is after I partitioned the model there, and then applied the bias, and then reduced the seeding.
Yeah, I see your email.
Started failing.
Okay. Let me just read this. Did you use the Python script, or did you go through the whole thing yourself?
No, I just did it myself.
Okay. Did it work once?
Yeah, it started working when the seeding was at 0.04, and I dropped it to 0.03. It worked, and then going less than that, it failed.
It failed. Okay.
Yeah.
Oh, okay. Yeah, I see. Actually, it's a disk space. And you remeshed it, right? So you didn't just, right?
Yes, I did remesh it.
When did it fail after a seeding density of what?
0.003. I mean, after 0.003, that's the next was when I was doing 0.002 really.
So 0.003 was fine.
Was fine.
And then 0.002 didn't work.
Yeah.
I can't remember if that was really small or not. Do you remember what I used in because there is going to be a memory issue on the computers, and this is not full version Abaqus, so it's definitely limited in a certain sense.
Oh, okay.
So you might be going way too small, and there's just not enough memory.
Oh.
You can as well. I don't know if this will fix your problem, right? But you can change your directory, right? So set work directory. So at the moment, whenever I've ran jobs on this version of Abaqus, I've just put it in my personal folder. So everybody has a folder, right? Just put it in there somewhere. I don't know if there might be more memory assigned to your personal folder than there is to the temporary folder.
Okay,
which is what it's usually, which is public temporary. That
so
might be.
You say, where do I go to change the directory?
I don't know if this will solve your problem, right?
Okay.
File, set work directory.
Okay.
And then save it there as well. So save your file there as well.
All right.
Yeah. But yeah, I I might just kind of get back to you on that. I might just check the different kind of seating densities that work, and
Oh,
like
okay.
if there's a limit. Can you just send me another email? Just the where at what seating density it didn't work,
Oh, okay.
and what was the last one that worked, just as a reminder. And I'll get back to you. It'll probably be, yeah. I'll try to get back to you tonight.
All right. Thank you very much.
Yeah. Um,
So this one, does it have like a submittable report also?
I don't think so. I'll just have a look. I think I've never actually gone through this course myself, so I'm not 100%. And I think Breffney might be changing it because of COVID and stuff. There used to be, I think the last year or two, there used to be so there was two Abaqus assignments. I think it would probably make sense just for future years to have more Abaqus assignments and less MATLAB assignments. I don't know if the MATLAB assignments are taking a lot of time on you for you guys. I'm not really sure. Might be good to have your opinion on that. But yeah, so for Abaqus there used to be two assignments. You've just done one, the mesh convergence one, and then I think there was a group assignment, which probably isn't going to work this year because you can't meet up.
Yeah.
So I don't know what Breffney's going to do.
All right.
Yeah. But it'll usually be to do with stents. So although there's no submission for this, definitely go through it.
All right.
Yeah. Okay. Yeah. If nobody has any more questions, feel free to sign off. I'll just hang out here for a minute just in case anybody does. But feel free to sign off whenever and stop recording.